Okay, so okay, I just make sure the microphone's on. Okay, so first of all, just a quick reminder: homework 9 will be due this Wednesday, and if you already saw the announcement that I made yesterday, then if you understand it, that's great. If not, then I'm going to address it again. So basically, what I said in my announcement about number 1 in homework 9 is the following. So if you look at the problem, it really, I mean, the problem doesn't include the picture. That's why there's an ambiguity here. So it just simply tells you that the chord A, B, and C, D, it's going to intersect at some point E outside. And then they want to prove that the two pair of angle are equal. Okay. So the problem is that because they didn't really say that it's a specific quadrilateral that in the circle or something. They didn't specific that what's the order of the chords, like the points. So what happened is that it turns out that technically there are two cases that you need to consider. So case 1, so once you fix the certain order of points, right? So for example, if in a circle, you have some chord AB, and you have some another chord, I don't know, like CD, right? So let's say if you fix this order, right? Maybe this is a bad point because I wanted to intersect, sorry. Maybe put CD so it actually intersect better. So let's say, okay, this is your, so once you fix a certain order, right? So either you can see that now my order is essentially, if it's like, if you read it clockwise, it's A, B, D, C, right? So it really doesn't matter whether you put A, B, D, C or A, B, C, D. Both cases work. So either, so someone asked me, actually, I think it's Derek, thanks to him, that it, because he asked me this question back during the weekend. So I actually realized that there's two cases we really need to consider. So first of all, either you can say the two cases are depending on how you choose the order of the points. So either you could do A, B, D, C like this, or you can do A, B, C, D. Then you can see that both either way it's going to work, and these are going to be the two cases we need to consider. Or if you don't want to considering switch the points, then you can consider the other phenomena where once you fix the order of the points, say, okay, I'm going to pick A, B, D, C, like what I wrote here. But when you set A, B, and C, D, the chord intersect at E, it could be either the case 1 where they intersect on the same side as BD, or case 2, either they intersect on the other side. So you still stick with the same order, A, B, and say D and C, right? But this time, let me make it not better. Sorry. So you can make it A, B, D, C, right? So then in this case, they're going to intersect on the left-hand side, on the same side as A and C, right? So that's why you should consider these two cases. Either you can say once you fix the position of A, B, C, D, or A, B, D, C, doesn't matter. Then you consider either they intersect at right-hand side or left-hand side. Or you can consider essentially like what I said, these two cases is reflecting to the two situation. So either you can say, okay, I consider A, B, DC. Bad picture, sorry. I couldn't make my mind. So do it again. So either you consider something like this, or some people would say my case 2 is essentially swap the order of point C and D. Right, so you can see that either you swap the points of C and D, that will give you two different cases, or you fix the position of C and D, but make sure that they intersect at different end. Okay, so no matter what, you're going to see two different situations. And I would say, like what I mentioned in the announcement or in the email, that basically you can see that you're going to use the same proposition. Okay, So you need to do both. So you need to do both because both the step is different. It's quite different, a little bit different. So one of them is slightly easier, where one of the angle is going to be like pretty much right away, right after using one of the proposition. But the other case, you need slightly more work, which involve using the fact that the sum of the triangle, the angles in the triangle is 180. So either way, you need to consider both cases. Okay, so either you can consider that you swap the where which end they intersect, or you swap the order of the point. So you're going to see two different cases and two different type of angles. Okay, so but in either case, you still need to prove both angles are equal, and you can prove it in both cases. So that's why when I in the that's why in the email I mentioned that you need to prove both cases. Okay, I mean the things that one of the case would be actually easier. So for example, case one, you're going to prove. So I want ACD, right? ACD equal to DBE, right? And then BCE is going to equal to DAE, right? So one picture it will be like this. But if you do the case two, then ACD is here, right? ACD and DBE. Sorry, ACD DBE. Did I? Oh, sorry, ACD ACE. Did I should say ACE. I think. Yeah, I think this is ACE. Let me double check. Is that ACE? I think I copied the problem wrong. Let me quickly check it. Does anyone can tell me right away? So this is 10.3.
Yeah, it is ACE.
ACE, right? Okay, thank you. Yeah, I think that's why I was like something's wrong. Okay, so ACE, let me fix this. Yeah, so ACE, so that would be this outside angle and this one, right? And the other one, BCE and DAE would be a bit different, right? So if you do BCE and DAE, so you can see that the case two, the shape or the angle it pick out will be different than case one. So I would say the case two is the slightly harder one, I would say, in this case, right? So either you can say I have case one like this and case two, or you can say the case one and case two would be essentially reflects or corresponding to swapping the order of C and D. Because actually, technically, the problem didn't really tell you what's the order of the chord, like the points. So I would say that I know I'm asking a little bit more, but I want to make sure that I could see people know how to prove both. But either case, I would say they're similar taste, like similar proof. One of them just need to do slightly one more steps. Okay, so that's one thing for the homework 9, problem 1. So especially if you already submitted earlier before I mentioned this, then you need to like make sure you submit it again. I mean, you can submit it anytime. So the case 2 will be harder. I think if I depends on which one. I don't remember which one is case 1 and case 2. If you swap in the point, one of them, yeah, one of the case would be harder, and then you can see that it's exactly the same thing, right? I forgot that if you swap in the point, maybe the case 1 is corresponding to which one. So I think, yeah. So I think that, yeah, if you swap in this one, the case 2 will be similar to this one, the corresponding. Yeah. So you're right. So the case 2, if you swap the points, the picture I show you here for the case 2 for swapping the points will be also be slightly harder, but it will exactly be the same. The angle you pick out will be the same, corresponding to like swapping the intersecting end. Okay, that's why either you can. So there are 2 different cases in general. Yeah. So that's why you need to show me both. So another thing I just want to address is that this is actually homework A, that when I was grading the homework A. So one of the problem, I think is the last one, they tell you that you have an outside point C where you have a tangent line, 2 tangent line, and then the tangent point is A and B. And let's say whatever you call it, the center is O. Then you connect OA and OB. So, and then also connect OC. So the first thing you need to say is that to recognize this angle is these two angles are right angle, or you can say OA is perpendicular to AC. And this is basically by proposition 3.18. So once you tell me that CA, this is because AC and BC are tangent lines, and OA and OB are radius. Okay, so you need to be careful that we didn't really construct this triangle to be right triangle. We didn't pick out to be a right triangle. It's essentially already kind of given there, right? So the thing is that once you know AC and BC are tangent lines and OA and OB are radius, then by proposition 3.18, we know that radius should be perpendicular to the tangent lines. So actually, when I grade the homework, some of you actually just tell me because it's tangent lines. Technically, it's not really enough, right? If you have something like, if you say you have a tangent line, but if your the other line is not tangent line, it's not radius. For example, if you have something like this, right? Let's say you have CA and then something like a DA here, right? Then of course it's not going to be perpendicular, right? So if you want to be very precise, then that angle OAC and OBC are 90 degrees is because AC, BC are tangent plus OA and OB are radius. If it's not radius, then it's not going to be perpendicular. Okay, so I want to make sure everyone knows about it, that 3.18 only works if you're talking about radius and the tangent line. So that's first thing, you realize that, okay, you have two right angle. So essentially angle OAC is the same as OBC, which is right angle. Then you also pointed out that OA and OB are radius. So a radius of the circle, so it's equal. Then also you have a common side, right, OC. Then in this case, then this is a right triangle, right? And this is exactly essentially you have a common hypotenuse and also equal legs, plus this is a right triangle. So this is essentially, we are going to use the hypotenuse and leg scheme. I noticed that someone called it different, but I would appreciate that if you use the name that we use this in this class. And also I noticed that someone called it, instead of calling it HL scheme, someone say it's the SSA for right triangle. Technically, I will give you a pass, but be careful, the usual SSA is not a congruent scheme. It needs to be a right triangle to be correct. So I would say to avoid ambiguity, probably it's better you just tell me it's a HL scheme, okay? For essentially that's for HL stands for hypotenuse and leg, right? So by this scheme, then we know those two triangles are congruent, then you prove like AC equals BC, okay? So even though this looks like a very easy questions, and it's exactly because it's easy. So when I grade it, I will grade a little bit harsh in the sense that if you miss just some explanation, I will take few points off because this is so easy that I want to make sure that you really know how you get those condition or evidence. Okay, so that's one thing I noticed. So just be a little bit careful here. So I think that's for now for the homework. So what I'm going to do today is that I only have a little bit left from 11.2, which essentially last time we talked about all these different centers. So we have in center, we have circumcenter, we have centroid. And the last thing we talk about, I think the most difficult one in some sense, the proof is most difficult, is the orthocenter. Okay, so remember that actually one of the homework you need to prove is to essentially fill in the gap of the proof for orthocenter. So the remaining thing I want to talk about is to just briefly mention that there's some spatial feature of orthocenter and also the other centers. And after that, I'm going to prove this extra material, which is essentially not in the textbook. This is Heron's formula. And I'm going to provide an algebraic proof. Okay, so then after this, then I will move on to chapter 15. So chapter 15 is basically about transformation, or in particular isometries. Okay, so I would say starting from chapter 15, it's going to be quite conceptual. In a sense, it becomes very abstract, like more or less like a mathematical proof. So I would say it becomes similar to maybe to 415 that you're taking. It becomes a little bit more math oriented in some sense. Okay, so first of all, let's see. So recall what's the definition for orthocenter. So orthocenter means you're taking the intersection of three altitudes of the triangle. And in this theorem 11.6, what we want to prove is that these three lines, those three altitudes, are going to intersect at a single point, and the point of intersection is what we call the orthocenter. So, for example, if you want to draw the picture, then let's see. So you have like a triangle here, and let's call it A, B, and C. Then let's say I want to draw three like altitude. So from A, I can have an altitude. From B, roughly, I can have an altitude. And from C, I can have an altitude here. So you can see that they intersect. Let me call this H to be the orthocenter. But of course, I mean, I always draw a acute triangle to be an example. I would suggest you, when you study all these four centers, trying to draw the picture for either right triangle or acute or obtuse, you're going to see that sometimes the center might fall out of the triangle. It's especially most of the time obtuse triangle, you're going to see something outside. As you can imagine one of the angle, because it's very big. So sometimes you need to draw an extension line or something like that. So you will see that some of the center is going to fall out of the triangle. Okay, so what's the special thing about this orthocenter? It turns out that there's a very interesting or actually amazing result, which I think I'm going to put this problem as one of the presentation problem. So I'm going to tell you more about presentation later on. There's some interesting exercise from the textbook that I will usually try to assign it as a presentation topic, because it needs a little bit more time to think about it. For some of the problem is longer, so it's actually suitable for a group project type of thing. So, but at least I can tell you what's the feature here. So when the orthocenter is not one of the vertices of the triangle, right? So if it happened, so this remark only works when your orthocenter H here is distinct from from any of the vertices. If this is the case, then these 4 points, the orthocenter plus the three vertices, they form what we call a orthocentric set. So the reason is that essentially, what's the spatial about these 4 distinct points? It turns out that each of the 4 points would become the orthocenter of the triangle formed by the other 3. So it's actually quite spatial, right? This is actually not so obvious at all to see it. I mean, the proof is not that hard, but from the first place, you would not know about it, right? Even just look at it, right? So what does that mean? For example, if you're using the picture I just drew, so this is the example I drew. If ABC has an orthocenter H, where H is not the same as any of the A, B, and C, then actually you can prove A is going to be the orthocenter of triangle BCH. And you can do it the same thing. B is going to be the orthocenter of ACH. C is going to be the orthocenter of ABH. So each one of the points out of those 4 points is going to be the orthocenter of the other 3. Okay, so this is actually quite, I mean, it's not hard to prove, but this is not something that we would think of it like at the beginning. So that's why we say it forms an orthocentric set. So it has like a spatial property like this. And another remark I want to make, which I'm not going to prove it, some of them you can kind of tell from the picture, but if you want to rigorously prove it, it needs some time. So it turns out that for an equilateral triangle, I mean, it's very symmetric everywhere, right? Equilateral triangle. Then it turns out that all the 4 centers that we just mentioned are going to be the same point. So orthocenter, centroid, in-center, circumcenter are going to be exactly just 1 point, the same point. They're going to coincide for equilateral triangle. You can kind of easily see it if you really draw like a precise equilateral triangle. And actually, the other way around also holds. If 2 out of these 4 centers coincide, then right away you can prove the triangle has to be equilateral, right? So this is kind of the converse of the statement, right? If you know it's equilateral triangle, then those 4 centers are going to be the same. But vice versa, if 2 out of these 4 centers coincide, then we also know that the triangle has to be equilateral. So that's why you can see that there's some significance of knowing all these centers, because in some sense, it also tells you a little bit information about how good, or in some sense, how symmetric the triangle is. Okay, so there's some good feature here. And the last thing, this extra thing, is also quite cool, but I'm not going to prove it. The proof is in the textbook. If you're interested in it, you can actually read it. They have some nice extra things, but we don't really have time to go through every one of them. So this is what we call the Euler line theorem. So it says if you have a non-equilateral triangle, okay, because if it's equilateral, then all the points are going to be the same point, then it's not interesting anymore. But if it's non-equilateral triangle, then it actually tells you the circumcenter, also center and centroid are going to be collinear, meaning they're going to lie on the same line. Actually, this is also not so obvious, but you can try to draw your own picture, right? But of course, you want to make sure that it's these 3 centers, the circumcenter, centroid, and also center. And those common line they lie on, it's what we call the Euler line. This is actually a surprising result, right? Because, I mean, how do you know? First of all, we actually need to prove that the existence of those 3 or 4 centers. Now, on top of that, we know if it's a non-equilateral triangle, then those 3 centers are going to lie on the same line. So that's what we call the collinear. Okay, so, I mean, you need to prove this. It's not so obvious at all. And the proof is in the textbook, but just as a nice feature, I want to mention, we can see this cool thing here. So, and the last thing I want to talk about for a 11.2 is this Heron's formula. So you definitely probably saw this in high school before, and there's so many different kind of proof we can do this. If I remember correctly, I've seen one of the not homework, but one of the exercise in the textbook actually has want you to prove the Heron's formula by using a different method, more geometric method. So, but here I want to show you at least the shortcut, in some sense, the quicker algebraic way to prove it. So what's the significance of this Heron's formula, right? So we all know how to calculate the area of the triangle if we know the base and height. But the problem is, what if we don't know the height, right? Then what you can do is if you don't know the height, then of course you cannot directly find the area of the triangle. But rather, if you know 3 sides of the triangle, right, then you can still find out the area. Okay, that's the significance of this Heron's formula. So the area of the triangle will be equal to the square root of this quantity S times S minus A times S minus B times S minus C, where S is essentially this quantity. S will be half of the sum of the 3 sides. Okay, so that's usually how people formulate this Heron's formula here. Okay, so now what we're going to do for the algebraic proof is that I'm going to use essentially law of cosine to prove this. So you can also view it as kind of an application for law of cosine that we know. Okay, so first of all, I'm going to do, again, I'm only using like a cube triangle, right? Of course, if you want to prove more rigorously, you should also show me this should be true for obtuse triangle, but it will be similar. So I'm just going to show you the acute case. But the idea is this similar using law of cosine. So you can see that, okay, so now, first of all, we still know that the area of triangle ABC is 1/2 if you call BC to be the base, right? So this is essentially BC times the height, okay? But now the thing is that I don't know explicitly what height is, okay? So the idea is I'm going to replace the height by something I already know, okay? By essentially the other 2 sides, okay? So now what would be the height here, h, right? So if you look at the picture I draw here, so I'm going to use the angle C here. So if you look at this right triangle A, and maybe call this point, I don't know, D, right? ADC, then the height h is essentially the opposite side of the angle C. So you can use sine essentially to write down, to replace this h. So in some sense, you can say h is equal to b times sine of the angle C, right? Or you can say sine of angle C is h over b. H, essentially, that's the opposite side divided by the hypotenuse, okay? But now, because I want to use law of cosine, so in other words, I want to rewrite sine in terms of cosine, okay? So this is essentially a little bit trick identity here, that we know sine squared plus cosine squared equals 1. So I can replace sine by square root of 1 minus cosine squared. Okay, so I believe that if you took calculus or a little bit like trick like before, then you should know this by now. Then now the thing is that, okay, I still want to represent or rewrite the cosine square in terms of the side, right? So now there's a lot of like trick of the algebra here. So first of all, I want to move to the side. I want to see how am I going to rewrite the quantity inside the square root, the 1 minus cosine square here. So first of all, recall the law of cosine. So be careful the sign, right? It's minus here. Oops, 2ab. So this is law of cosine, right? The side c squared would be equal to a squared plus b squared minus 2ab times cosine of the angle C. Okay, so now that's C. So I'm going to rewrite the cosine, okay, because I need the cosine of this angle C. So this is going to be, I'm just rewriting things, right? Okay, so you can see that if you just algebraically rewrite everything, then cosine of angle C is going to be a squared plus b squared minus c squared divided by 2ab. Okay, now you can see I need 1 minus cosine squared, so I'm going to square it. And if you square the bottom, the denominator, it's going to be 4a squared b squared. Okay, now that's C. Then I'm going to do, because this quantity inside the square root is 1 minus cosine squared. So I'm going to take 1 minus cosine squared. Okay. So now, I mean, I want to rewrite 1 in terms of the same common denominator, right? So you can see that we're going to have something like this. Okay, right? I just rewrite 1 in terms of 4a squared b squared divided by 4a squared b squared. Okay, so it's really pure algebraic. Okay, so now that's C. So now I'm going to plug in what I just wrote into what we had here. Okay, so now that's C, right? So okay, so now I'm just continue the equation here. Okay, so first of all, I'm going to rewrite this quantity like this. So I'm going to put everything under square root, right? Because Heron's formula in the end, in terms of square root, everything's under square root. So I haven't plugged in yet. I'm just write down everything in under the square root. So essentially I put 1/2 AB inside the square root, right? Okay, now I'm going to really plug in. Actually, I should say, then probably I should do this. Okay, now I'm plugging in and see what happened. And then essentially now the rest of it is just more or less like algebraic, like simplification. Okay, so now I keep a squared b squared and I keep this 4 here. but I'm going to replace 1 minus cosine squared by what we just did here, right? So essentially I have a 4a squared b squared minus a squared plus b squared minus c squared to the perfect square. And I also have another 4a squared b squared here, right? So essentially I just plug in everything that I just did using the law of cosine. Okay, and you can see the reason, the good thing is that now after you do that, then you have a squared b squared that can cancel out from the numerator and denominator, right? And the bottom part becomes 16, okay? So keep the 16. Okay, so now I have this part 4a squared b squared. I'm going to rewrite it as 2ab to the perfect square. And I keep the other perfect square here. And the a squared b squared cancel out, so we only have 16 in the bottom. Okay, let's do it one by one. Okay, so now we come to use another trick here. So you can see that the numerator is perfect square minus perfect square. So I'm going to use this, let me put it here. This is another algebraic identity, right? So you know that if you have something perfect square minus another perfect square, this is the same as a plus b times a minus b, right? So you have a perfect square minus another perfect square. This would be the same as the sum times the subtraction, right? This is something we kind of use it all the time. So I'm going to do it here, right? So you can see that you have a perfect square minus another perfect square. So I'm going to essentially doing this trick here. So then I'm going to rewrite a lot of things. Okay, so now let's see. So if you use this, then the next step would be the following, right? So I need to keep the 16 in the bottom, but the numerator, it's going to become 2ab plus a squared plus b squared minus c squared, right? Times 2ab, right? Minus the other thing. Right? So I just rewrite the subtraction of the perfect square like this. This is really purely algebraic, okay? So now let's see. Now we simplify, right? Okay, so now let's see. I have let's say 2ab plus a squared plus b squared. This is going to be perfect square, right? So I essentially kind of that rewrite things and then rebundle it together. So this is essentially a plus b to the perfect square. Okay. So I have a plus b to the perfect square minus c squared. That's the first thing. Okay. And this thing here, if you look at it, it's going to give you minus a plus b to the perfect square. Right? If you think about it, then this would be the case. So that would be minus a plus b to the perfect square minus c squared. Okay. Actually, the plus, sorry, plus, minus, minus, plus. Okay. Now I have, just keep the 16. Okay. Now we're almost done because now you can see that the way I rewrite everything, I essentially break the things, right? I use the identity to break things, but I kind of rebundle it again. So I have another type of perfect square like this. Now I'm going to do this again, right? Because now you can see I have perfect square subtract another perfect square. Perfect square subtract another perfect square. So I'm going to redo it again. So this is, you did it again. Okay, so now this becomes a plus b plus c times a plus b minus c. So I essentially break the product into more product. And this is the first one. And the second one you have the subtraction of the perfect square. So you can break it into C plus A plus B times C minus, did I do something wrong? Actually, sorry, I think this should be minus here. A minus B, sorry. Right, because this is actually A minus. So let me double check, right? So A minus B squared, this is minus A squared minus 2AB plus B squared. So this is minus A plus 2AB minus B squared. Yeah, should be minus there. Yeah. Okay. So now let's see. So I have C plus 2A minus B and C minus A minus B here. Okay. So now we have 16 in the bottom. Okay, one last step. Okay, this is really just keep rewriting things. So one last step. I'm going to rewrite this into like four products together. So the first one is A plus B plus C divided by 2, right? I just keep it. And I'm going to rewrite A plus B minus C as something minus something. So I'm going to rewrite it as A plus B plus C minus 2C divided by 2. Right? Essentially, I'm breaking 16 into 2 times 2 times 2 times 2. Okay. And I'm going to do the same thing here for C plus A minus B. So this is going to be A plus B plus C minus 2B. And do the same thing with the last one. It's going to be A plus B plus C minus 2A. The reason I need to do that is because I need to see the S over there, right? So remember, S is what we call the half of the sum, right? So if I want to come up with this thing, so I can use the sum. So if you plug in the notation, this is exactly S times S minus A times S minus B and times S minus C. That's how we prove it. Okay. So actually, I mean, I'm doing kind of step by step because I want to make sure that you can see the process here. But essentially, it's really pure algebraic. In some sense, it's using law of cosine and then also this algebraic identity twice, I will say. And then you just really simplified it and trying to get to the format of the Heron's formula. So I know that, I mean, from my memory, I remember seeing this formula when I was, I mean, in high school, for example. So I think that it's also important for a future teacher to see some of the proof. But as I said, there should be other proof of Heron's formula. But this one is the pure algebraic one. And then once you know the law of cosine and some algebra here, then this is actually, you can directly prove it. Okay. So this is one type of proof. And yeah, so this is not in the textbook. So you only see it from here. Okay. Is there any questions so far on this one?
Can you just scroll to the bottom so I can see?
Oh yeah, sure, sure. Yeah, here. Okay. Yeah, I'm going to post the notes later on as well. So I mean, everything I wrote down here, you can find it on Blackboard. I'm always posting the notes. So I mean, I appreciate that you want to copy your notes, but like, don't worry about having to copy the notes if you don't have time. Yeah. Okay, so can I move away?
You're good.
Okay, yeah, good. Okay, so now let's see. So as I said, I'm going to move on to the chapter 15. So I need to warn you that 15 can be quite abstract, or the proof can be difficult, but this is definitely more math oriented. So, or I don't know, in some sense, it's kind of algebra, but also at the same time that it combines some fact that we want to prove in terms of geometry. But before we can prove certain fat in the geometry, we need to consider some of the algebraic structure here. So at the beginning of the chapter 15, or actually like 15.1, they actually mentioned this very important definition in algebra. So if you're a math major, like if you took some extra course, you might at some point take like a college, like not college algebra, like abstract algebra. Okay, so then this would be probably the first thing you're going to see. Okay, so or maybe you already saw that in some other subjects. So we're going to define what a group means. Okay, so a group is a collection of elements, or you can say it's a non-empty set of elements, and that's called this capital G, stands for group. But the group is actually more than just a collection of things. It's actually, you need to pair with an operation. And this is what we call the binary operation. So binary means that you say element A is acting with B. So it's essentially discussing the relationship between two elements. So we call it binary operation. And since we don't know, this operation can be general in the sense that that it can be the addition we usually know of. It can be multiplication. It can be any operation that you want to define. Okay, as long as it makes sense. So that's why in this textbook they put this notation like a small circle to be more like general, right? It's not necessary addition or multiplication or division. As long as that it's the operation you want, you can put it there. So first you need to have a collection of elements together with an operation you want. Then you need to in order to be a group, you need to satisfy, like this whole thing need to satisfy 4 criterion. Okay, so if you still remember something from the linear algebra, you still remember that back then they checked like what counts as a vector space, right? There's all this axiom, right? So same thing here. It's a little bit similar, but not exactly the same. So the first criterion that for any elements A and B, any 2 elements A and B from your collection, when you do the operation between those 2, then after you do the operation, say A acting with B, then the new element, right, A acting B, maybe it's something new, right? It's different. If you think about the operation as addition, then A plus B will be a new element, right? Then this new element should be in the collection, right? So for example, if you have some collection G, right, you have a whole bunch of elements, right? And let's say one of them is A, the other is B. You need to make sure after A acting on B, it still lies in the collection. If the collection is too small in some sense, then A acting B might fall out of the collection, right? So that's why you need to make sure that A acting B or A operate with B still lies in your collection, the set G. So that's the first thing. So sometimes we call this that it's the set is closed under this operation. This is also sometimes you will see people say that it's closed under addition or depending on what the operation is. The second thing is that if you want to be a group, then you need, if this set, you need to identify the so-called identity element. And usually we use a spatial notation for identity element. We use small e. So it means you need to find this identity element from the set G such that it satisfies this criterion. So if acting on the identity should be equal to be E acting with A, and eventually it should be the same as A, right? So you can imagine if this operation, circle operation is addition, then your identity should be 0, right? The 0 element, right? If you was think about, okay, like real numbers, right? Then you can say and then your operation is addition, then it becomes the identity element will be 0, right? And this this equation should hold for any element A in G. Okay, so that's essentially you need to have identity element in your set. And the third criterion is that after you identify the identity element, then the next thing is to find an inverse for every element. And your inverse should also in the, not only you need to find the inverse, the more important thing is that for each element, you should have an inverse, which also can be found within this set G. Okay, so that means for each element A in this set G, you can find another element B, which is essentially what you call the inverse, such that A acting B is the same as B acting A, which is essentially the identity. So in some sense, in order for inverse to even make sense, that's why we first thing we need to find the identity. Once you have the identity element, then you can define what the inverse is. If you don't have even like an identity element, then forget about finding an inverse, right? It doesn't make sense to talk about inverse without an identity element. So now if you know that there's an identity element, there's an inverse, which is also in G, then the last thing is usually the most easy to check. You want to make sure your operation is what we call the associative. That means if you do B acting C first, and then acting with A like this, it's the same as doing A operate with B and then operate with C, like in this order. So this is like an associative. As you can imagine that most of the operation we saw, like the common use one, right? Addition, multiplication, this is definitely true, right? If you have a number A plus B plus C, it's the same as A plus B, then plus C, right? So you can see that depends on the operation. You need to check through this for criterion. And of course, you can have the same collection, same set G, paired with different operation, right? So for certain set G, if you pair with addition, it will give you a group. If you pair with, say, multiplication, it may not be a group anymore. So that's why the operation you pick here is very important. So it's like a whole package. Not only you need to consider the set itself, you also need to take into account what operation you're defining here. Okay, so right away, let's take a look at an example. We actually know a lot of group here. So first of all, I claim that the set of integers, sometimes that people use like capital Z as a set of integers, right? With addition, you pair with addition as an observation, then this whole thing is a group. Okay. So let's check why this is true, right? So that's really goes through criteria one by one. So first of all, let's say you have all two integers, right? So your collection is all the integers. Okay. You want to make sure if A adding B, in this case, is addition. So you want to make sure that once you add up two integers, it will still lies in the set, which means it will still be integer, right? So check the first criterion. So for any two integers, A and B, right? We know A plus B is also an integer, which means A plus B is in the set, right? So that's why the first criterion is okay. For any two integers from the set, after you do the operation, it will still lies in the set because they're still, the new thing is still integer. Integer plus integer is still integer, okay? And be careful, integer can be negative, right? So integer, the definition of integer is 0, 1, 2, 3, 4, 5, or, and so on, or 0, minus 1, minus 2, minus 3, everything, right? As long as it's like integer. It can be 0, it can be negative. So now second thing, I want to find an identity element. And so in this case, because my operation is addition, so as I said, if you want this criterion, the second criterion to hold with addition, then you can imagine that it has to be, the identity element has to be 0. So essentially, 0 is the identity element of the set of integer, right? And you can check, we need to check, right? Because 0 plus any integer will be the same as integer plus 0 is A, right? So A is any integer. Okay. So this is I mean easy to see, right? Because 0 plus anything is equal to itself. Okay, so we know that we really find an identity element, which is 0 in our case, from the set. Third one, we want to find the inverse. What's the inverse in this case? It means if you give me an integer and you want to find that integer plus something, it's going to be identity, which is 0. And this is essentially if you say 2 plus something equals 0, then you know that something is -2. And -2 is also integer, right? So you can see that essentially the third one is for any integer a, right, from the set of integer, we can find an inverse, which is essentially -a, right, from the same set z, right? Because minus a is also in, if you have integer, the minus of that integer will also be integer, right? So then essentially, like we know a plus minus a is going to be the same as -a plus a, which is 0, right? So we really check that there's an inverse element from the same set, right? Then the fourth one, the addition, is definitely, I'm not going to check this, the addition as an operation is associative, right? You can say that a plus b plus c, like what I said, is the same as a plus b plus c. So you can see that the collection of all the integers paired with addition as an operation will form a group because I check through those 4 criteria. And as you can see, this become more abstract because you really need to check through a lot of things. So the next couple example, I'm not going to do very detailed because I mean, it's going to take up too much time. So for example, another example would be if you only collect even integers with the addition, it's also going to form a group. So you can actually check it yourself that, I mean, doing like what I just did, right? Check all the 4 criterion here and trying to see, in this case, because you can see that the operation is still addition, so the identity element definitely will still be 0. And the inverse will still be even integer, right? So even integer means like 2, 4, 6, or 0, or -2, -4, -6, and so on, right? And you can see that, I mean, 0 is an even integer. That's why it's a 0 element in this set. And you can see that if you have even integer, then you can definitely find the inverse, which is the negative of it, and which is also an even integer as well. So it's pretty much the same proof as the first example. Okay, so it's not too bad. And also we can see that the set of non-zero rational numbers are going to be but this time the operation becomes multiplication. It's going to form a group. So if you don't know what rational number is, I mean, I don't remember exactly which course we are going to learn rational numbers, but rational numbers means if you have any integer over integer, then that's a rational numbers. But in this case, we are going to collect all the non-zero ones, so we cannot include 0. So that's why P and Q should be non-zero integers in this case. So if you have any non-zero integers over non-zero integers and you collect it, this set along with the multiplication is going to form a group. Then in this case, the identity element is 1. 1 is a rational number, right? So now you can see that if you change the operation, it's going to, like the identity element may change, right? So in this case, the previous one with the addition, identity element is 0. Okay. Now, of course, I want to show you not every collection of numbers or whatever elements are going to form the group. So for example, if we still take the integers, but this time we switch to multiplication, it's not a group anymore. Okay, so the question is why this is the case, right? So first of all, you can think of integer multiplied by integer, it will still be integer. So the first criterion should be fine. So the first criterion is okay. Second criterion, you want the identity element. 1 is an integer. 1 times any integer will be itself. So you actually have an identity element. So number 2 is also okay. So identity element is 1 in this case. So it's actually fine. But now number 3, you want to find an inverse corresponding to multiplication, right? You want something times an integer, something times multiply an integer to be identity. Now you realize that something should be 1 over a, which is not an integer anymore. So you cannot find the inverse. If you want to find the inverse, then it's fall out of the set of integers. That's why this would not be a group anymore. And multiplication we know is associative. So the problem is actually this number 3 criterion does not hold. So you should do this kind of practice to familiar with the definition of the group. So later on, like after we do a little bit further things, I'm going to assign like some question where you really need to use the definition of group, okay? So someone asked me elaborate on which example, the number 4 or 4.3? What do you mean 4.3? Like, oh, you mean like why this is not, why the number 3 criterion is not okay. So the thing is that if we go back to see the third criterion, so we agree that we have an identity, right? That's the 1 in this case. But number 3 criterion, you need to find an inverse from the set, okay? So in this case, what's the inverse here, right? So let me put it out here. So the thing is that for any integer a, right, from whatever this collection is, you want to find a number b from the, let me take this out. You want to find a number from the same set such that a times, because now we are doing multiplication, right? The operation is multiplication, equals identity. The problem is that if a is an integer, then the only way is b should be a fraction number, not the integer anymore, right? So if a is an integer, you can find the inverse, but the problem is inverse would not be in the set. That's the problem. So the inverse is not in the same set anymore. So that's the problem. You can, of course, find some inverse, but that inverse is not in the set. The whole point is that you should be able to find inverse from the same set. That's the issue. Okay. Okay, so that's why integers paired with multiplication is bad in the sense that, I mean, it's just multiplication will ruin everything. Addition is fine because you can add, subtract things in some sense, right? But like multiplication, then you will create some fractional number here. Then it's not integer anymore. Okay, so there are so many other examples, right? If you seriously Google everything group, right? Or I mean, find a Wikipedia, there's so many type of set that will form a group. Group should be a general thing. Right now, I'm playing with all the possible like numbers here, right? But you can also have some other general things, not necessarily a number. It will still form a group. So anything, any collection and any operation you define, as long as it satisfies those 4 criteria, then it gives you some kind of like nice structure. And this is what we call the group, okay? So now keep this in mind. Later on, we're going to see like a lot of example here. So actually the main point for chapter 15.1, or actually the whole chapter 15 is actually talking about rigid motions, or what we call the isometry. Okay, so later on, you're going to see the collection of all the isometry functions are going to form a group. That's why isometry is nice, because it has a nice structure, algebraic structure. You can think of group provides you a nice algebraic structure to work with. Okay, so first I need to tell you what isometry is, okay, or what rigid motion is. So it depends on that, what's the domain that you're talking about. Then isometry, like, I mean, we use maybe slightly different definition here. So if you're talking about isometry as from a real value function, then we can say that generally isometry is any function that preserves the distance, right? So if you take like a function of one variable, that's real value function, one variable, actually one variable, right? Then it means you want this function to preserve distance. So that means the distance from x1 to x2 will be the same as distance from f of x1 to f of x2, depending on what the function is, right? So you can see that, but this should be true for any x1 and x2 in the domain, right? So for example, I'm just making first like easy example, like one variable function, right? So I claim f of x equals minus x. This function is an isometry from real number to real number, right? So you can see for any real number, what's the distance between two real number? It's just you take the subtraction and take the absolute value, right? So you have 5 and like I don't know, like 2 and minus 3. What would be the distance? It would be minus 3 minus 2. Take the absolute value, right? So if you look at the absolute value between f of a and minus f of b, right? But you can see by definition of the map, right? We know f of x should be minus x. So what's f of a? F of a is just minus a, right? F of b is minus b. And if you take minus a, subtract minus b, and you take the absolute value, it will be the absolute value of b minus a. This essentially equal to the distance between a and b, right? And then this part on the left-hand side is the distance between f of a and f of b. So that's why I know this function is an isometry. And technically, I actually are not done yet, because the definition we are going to use for isometry, or essentially, is stronger, okay? But technically, isometry is a map, which is, I mean, I want to tell you the definition later on, but I can tell you now that we want a stronger definition. Not only we want it to be distance preserving, we also want to require it to be a surjective, onto map, okay? So we're going to see more, like a more rigorous definition we're going to use later on. But this is essentially a first example. If you're talking about real value function, then we can easily come up with a function that preserves the distance. I mean, this is actually easy. You can cook up with a lot of functions that's going to preserve the distance, okay? But because we're talking about geometry here, so we want to talk about a more like a different situation where I want the domain to be R2, to be anything on the plane, right? Because we're talking about plane geometry now, right? We talk about triangle, circle, everything's on the plane. So first of all, we want to give a spatial name to any function from a plane to itself. So from R2 to R2. Such a function, we give a spatial name. We call it transformation, or sometimes people say it's a mapping, but most of the time people say it's a transformation. So any function that's from R2 to R2, we give a spatial name. We call it transformation. Okay, but we don't know whether it preserved the distance yet. Okay, because I didn't say it's isometry. I say it's a transformation. Okay, but before we define isometry, I want to point out several terminology that you're going to see from now on till like throughout the chapter 15. So if A is a point in R2 in the plane, such that f of A equals A, then we say this transformation f fix the point A. Or sometimes more commonly, people say A is a fixed point of A, F, sorry. So in other words, A is a very spatial point, right? We know that in general, if you have a map from R2 and to R2, it's not always the case that you plug in the value, it will come out with itself, right? The input and output may not be the same point or same value. If it is the case, then we say it's a fixed point. Okay. So later on, you're going to see that sometimes that we are going to use this terminology a lot. Okay. And also we can define what we call the identity map. Okay. So identity map, we use spatially this small I or script I. So identity map is a transformation that fixes all the points. Meaning if you plug in any point, it will come up with itself for any possible point. So in other words, essentially, maybe this makes you feel better. If you want to use X as a point, that means I of X equals X for any point in R2. Okay, right? That's why we call the identity map. Okay, so or if you want to use more fancy language, identity map fix every point, right? You can say that as well. So it's a transformation fix every point. Okay, so this is essentially that some terminology. So another remark I want to make is that once you have essentially two or three, whatever, like some transformation, you can create a new transformation. So essentially, I don't want this color, I want blue one. So essentially, we can create new transformation by using composition, right? By composition of functions, right? So composition of two functions. For example, we would say we use this notation, right? Compose G, right? You first plug in A, this point, into G. Then you plug in, so this is essentially, I mean, this is actually Calc 1, right? We've seen that composition of functions or maps or transformation, right? So you plug in A into G, then you plug in G of A into F, right? So then F compose G is another new function, right? Or new transformation, doesn't matter, right? But one thing you want to be careful is that in general, F compose G is not the same as G compose F, right? So the composition, this action or operation is not commutative, right? We all know that if you do F compose G in calculus, this may not necessarily be G compose A. You can easily, G compose F, you can easily check it. So you want to be a little bit careful unless you know that you're doing some other nice operation. Otherwise, you should not directly switch it, the order. It may not be true, right? For example, 2 minus 3 is not the same as 3 minus 2, right? So we know that you cannot easily switch the order. So now finally, I can introduce what isometry is. So in this case, in the context of our like plane geometry, we say an isometry or a rigid motion is a transformation, meaning a map, a function from R2 to R2. So a transformation from a plane onto itself. Okay. So not only it's a map from R2 to R2, you want the map to be surjective. So onto also means surjective, right? And of course, we want it to be preserve the distance. And distance preserving means, again, if you have any 2 points A and B in R2, then the distance between A and B should be the same as distance between F of A and F of B. That's what we meant, the distance preserving. So technically, there are two things you need to check for a transformation to be an isometry on R2. First, you need to check it's an onto map. It's a surjective map. Second, it needs to preserve the distance, like what we wrote here. So I want to recall the definition for onto because I'm afraid that, I mean, I don't know how much math course you have taken and like maybe you forgot about what surjective means in terms of like mathematical equation, right? So I put it as a note here. So f of map or any function, doesn't matter where it is, it's onto the whole R2, or you can say it's surjective, same thing, means that for any point in R2, you can find another point C such that f of C equals D. So in other words, let me show you this picture here. So you can think of that f is a map from R2 to R2, right? What do you mean by onto? That means if you pick any element from R2 here, you want to be able to find D from the, like R2, you want to be able to find C such that C can get mapped to D. That's what it means by surjective, right? You will always account for, you can find what we call the pre-image, right? So this is essentially the definition of being a surjective or onto map. So for example, anything in R2, you can find a corresponding things in the domain such that it get mapped to the target we want. That's onto, that's surjective, okay? So, I mean, I think if you take some abstract math course, they definitely will talk about onto or surjective map. I believe in calculus, we should have seen this before. So essentially, isometry is an onto transformation, or you can say a surjective transformation to R2 that preserve distance. So actually, onto is easy to check most of the time, but you need to check the distance preserving. That's a little bit more work, okay? So before we end, I'm going to just use this example. So let's say this is actually more like a not geometric example, but I mean, you can cook up with a lot of this type of functions. So let's say if you plug in x1, x2, that's a point in R2, then the output is some kind of shifting, right? So this is, you input a point in R2, right? And this is output is another point in R2. I want to show that it's an isometry. Okay, so first I'm going to let you prove it yourself as an exercise. Prove this map is onto, meaning any points in R2, you can find a corresponding pre-image. Okay, that should be easy to check algebraically. But I want to show you at least the part for checking the distance in preserving here. Okay, so I think that check f preserve distance. Okay, so now first, what's the distance between f of x1, x2 and f of y1, y2, right? So you have, essentially you can think of, you have f of a and f of b, right? Those are 2 points, and you want to find the distance. So you're asking about the distance between these points, x1 plus 1 and x2 plus 2, and another point, y1 plus 1 and y2 plus 2. Okay, so think about you're in R2, you have 2 points, okay, with 2 coordinates. How do you calculate distance between those? You use the usual distance between 2 points in the plane, right? So you take the subtraction of the first coordinate and take it square, right? Plus the subtraction between the second coordinate and take square, right? And you can see that after you simplify, because they all have the same shifting here, right? The first coordinate is going to shift by 1. Second coordinate shift by 2. So after you do the subtraction, you don't see the shifting kind of. So then you will get square root of x1 minus y1 squared plus x2 minus y2 squared, and which is exactly the same as the distance between the point A and point B. So that's why they preserve the distance. If you want to see the picture, then in some sense you can see that, okay, if this is R2, right? Then you will have some points here that say this is x1, x2, right? And then you have, I don't know, some other y1, y2 here, right? And then you get mapped to, let me push it a little bit forward here, sorry. And then you get mapped to, say, you shift it, right? This is some kind of shifting. So you want x1, and so you go shift 1 by x, and then 2 by, so maybe like here. So this is x, maybe a little bit here. So this is x1 plus 1 and x2 plus 2, right? But you do the same thing with y1. So y1 is original here. That's shift a little bit high up. Right, so you can see that the distance between these 2 points should be the same. I mean, I didn't do the picture very well, but you can check it should be the same. So maybe the point should be lower to maintain the distance. That's better. Yeah. So you can see it's some kind of translation or shifting, right? So you can, because I give you an explicit function, so you can really check it. But imagine later on, we are going to do a little bit more. We're going to essentially do like a more abstract geometric map. For example, I can tell you it's a translation, but the way I define translation is not explicit map, but rather tells you geometrically how to do a translation. Or we can do like a rotation, right? And then everything is going to be more geometric. And then you're going to use a lot of like geometry fact that we know, right? If you're trying to prove the distance is the same, then you're going to maybe show that two triangles are congruent, and then you can prove two sides or two lengths are equal. So you can see that it's more like combining the geometry we learned earlier and some algebraic fact in some sense. Okay, so I'm going to stop here. So next time I'm going to come back to talk about a little bit more about isometry, and then I will going to tell you that what's the good property come out of isometry. Then I'm going to really introduce that essentially there are so many different kind of isometry, like translation, rotation, and so on. Okay. Okay, so if any questions, feel free to stay. Otherwise, you're free to go. And don't forget, there's a homework you want to start as early as possible.